He doesn't get to choose. He's not here. You guys get to choose who gets to answer. Do you want to rock, paper, scissors for it? Okay. Rock, paper, scissors for Andrew. Team captains. Rock, paper, scissors again. This is your chance, Will. Best 2 out of 3. You lost again. Yes. So you get Andrew.
I think she's taking PEDs. Can we check
She's doing what?
PEDs.
Performance enhancing drugs to help her win it.
I mean, all I'm saying is 2-0 right now.
It's really funny. Is one of my sons. We would do lots of rock, paper, scissors, and my younger son almost always wins. And then he leaned over one time and he goes, "Watch it. He always does paper at the beginning." And then he figured it out. He always does paper at the beginning. And it's just a. And we even told him, and he still does it. It's because then then you start playing well, maybe he's gonna think that I'm gonna do paper, but I'm not gonna do paper, and then it's a mental game. Tony's got you beat twice now, Will. Okay, so here's VCI, right? And again, look at these terms in here. There's a lambda, we know what that is. BW, even that isn't going to be super clear because depends on in your homework it's a double T, and then with the web that's tapering, right? So even almost immediately, what do you do for the BW? VI, I don't even know what the hell that is. Okay, MCRE is an equation. You look up the MCRE equation, there it is right there. Son of a bitch, right? And then, but then there's, again, some simplifications that you might be able to use as you go through here, right? So it's VCI is either this one or this one. So it's the flexion shear shall be the greater of. So you grab the greater of this one or this one. So just VCI you have to put in a max on both of those things, okay? Then you keep going, right? And then this MCRE that shows up in that equation up there, that's what you use as the MCRE equation. Oh, there's a YT right here, right? We got to figure out what that YT is. We got a lambda. We got an FPE. I don't know what that is. An FD. I don't know what that is. That's what you'd be looking up in the nomenclature sections. It'll tell you what each one of those things are, and you have to go and read them and say, what the hell do those mean? That's kind of some of the stuff I'm going to go over today. Okay, and again, some simplifications that you may be able to use. I got this arrow here. You must be able to use that simplification. But you can read the stuff over on the right, and it'll tell you. If you can, use the simplification. I'm pretty sure you could use that one, but maybe just put an arrow to it with a question mark. This is from last time I taught it. Okay, VCW shall be calculated by this, right? Again, some other variables that are showing up in here, right? What is the VP value? And so it'll tell you all that stuff throughout. As an alternative to it shall be permitted to calculate VCW as the shear force corresponding to the dead load plus the live load that results in principal stresses of this at locations A or B, right? So hopefully you start seeing this is a bookkeeping, logic, confusing as hell assignment, right? Like I said before, this is probably one of the worst you've seen once you dive into it, you'll see. Once you dive into it, this is probably one of the worst you've seen in concrete. Is there some bad ones in concrete that took concrete last year? Is it the whole class like that? Concrete 2 in particular, yeah. There's just so much. Yeah.
And the code for the
Yep. So those of you that have taken concrete 2, maybe this will be easy for you because you're used to using ACI values. Okay. VS that you get from the steel, right? You can calculate what the VS is. And then VS, you can calculate as this, right? AVFY D over S. I saw that they tied cages in the last time, in the big beam from 10 years ago, whatever it was. They tied a cage, and I wonder if it's because they failed the shear capacity, so then they had to put in stirrups, right? You're okay. You don't have to use shear stirrups in your beam design if you don't need them. If it works out for the calculations without the stirrups, great. But if it doesn't, you have to put in some stirrups, right? And then the capacity of the stirrups, or the capacity that the stirrups add, are just simply this, AVFY D over S. Right? Same thing as that you use for regular reinforced concrete. And you could specify the spacing and stuff like that that's required. So here's your homework. Okay, calculate the shear capacity from 8 an 8 double T 24 with 128 D1 tendons on a 60-foot span using the provisions of ACI 22.5.8.2 and 22.5.8.3. So this is the approximate approach, do that, and then there's the approach where we do the VCI, VCW, and grab those differences. I tried to explain. I used to think that this was enough to explain, but it never was. Use an FPE, effective pre-stressing stress in the steel that includes pre-stress losses of 165 KSI. That's actually, you get that from the code from the PCI. Note that the ACI calls this variable FSE in their equation. So what we're calling FPE, they use FSE in ACI equations. Okay? They have their own, and then this makes it even more confusing, they have their own FPE. We have an FPE that I gave you from our formulation of stuff. They have their own FPE, so you have to be careful with that. What else does it say? It says, shear defined in the notation section causing ACI's FPA is defined in the notation section of the ACI. Allowable service loads for this beam. For the demand in this problem, factor the maximum allowable service load from this beam and the span. So you're going to have to look at the PCI tables, and that's their load tables for different spans. So you can look up what the allowable load is that you can put on top of this thing. And that's the allowable load that you can put on there. I think it's just I think some of it's applied dead load and some of it's applied live load. It tells you in the text what that load means, and then you'll have to add on to it the self weight of it as well. Right? Both of those things in, and then that'll be the demand. And the reason you're going to plot your demand on there is just to see if your capacity is greater than your demand. That's what you're making sure. So you're going to have a line on that. I'll show you what the solution looks like. Note that the maximum allowable load for this table is service load, and that the controlling load probably comes from an other limit state governing the pre-stress beam. So most likely cracking. Okay, and then plot your results as a function of position along the span, including the factor demand when the beam is loaded at the maximum load. Okay, so then this is what the answer is. Okay, and then you have it there. So then this would be very similar to what you did. This would be very similar to what you did in the last homework where I gave you the solution. You just keep going until you get this, right? This is what it should be. Right? The black out here, this is the more complicated method, VCI, VCW method. And then this one right here is the approximate method. And like I said, right, the more advanced method, the harder to implement ends up being, the harder to implement is less conservative. It says you can go to a capacity of 70 kips as opposed to like 48 kips or whatever that is. Okay. Note this little uptick over here. Right? They both kind of like, this lower one, I think this is the 2 square root F prime C is what these values are down here. But it increases a little bit the tail end. And what that is that D limit. Remember the D, it says the D need not be less than 0.8 H. That's what this is. So basically everywhere along here, the D is less than 0.8 H, except for right here, it starts getting bigger than 0.8 H, and then you could use the bigger D value for that. And that's why it starts increasing, because this is a heart section, right? It comes down, the EP comes down like in a heart. And so near the middle, you're gonna have bigger depths down to your steel, and then that's why it starts increasing. Everywhere else, it's the 0.8 H control. So then that'll be one of the columns, right? I would even have a column for D that you use, and it's just gonna be what the actual D is, and then limiting at 0.8 H, and then so you'll have a D affected that you use throughout. Okay, that's what you're aiming for. Okay, so some variables. Their FPE, right? So this comes right out of the notation section. Their FPE in ACI says compressive stress in concrete due only to the effective pre-stress force after allowance for all pre-stress losses at extreme fiber of section if tensile stress is caused by external applied loads in PSI. What the fuck? This is what I'm saying, right? What's going on? The other thing to be very careful, I just want to state this, if it's not written on there, write it as so. All variables in ACI go in as positive numbers. If we're talking, this is a compression stress we're going to get, so your methodology is going to be a negative number, but when you put it into ACI, it goes in as a positive number. Right? And so I would say it was this. So compressive stress in concrete due only to the effective pre-stress forces after allowance for all pre-stress losses at extreme fiber of section if tensile stress is caused by externally applied load. So, but basically that's saying for this is this part right here, at extreme fiber, externally applied load causes. So this would be at the bottom. They're just saying at the bottom. Under a simply supported beam, right? Loaded due to gravity, a simply supported beam, the applied load is going to cause tension at the bottom. That's what the second part of the sentence is. So it says, what is the stress down at the bottom? And so if it was the other way around, if you were doing negative, if it was a cantilever sticking out and you're applying the load, then it would be the bottom. It would be the top, right? It'd be the top because that's where the tension, by applying the load, it would cause tension at the top. And so it means the top. And so the reason it goes through all this is to account for that. So it's just the stress from the pre-stressing after the pre-stress losses. So it's just this, right? Negative FP over AC minus FPEP over S1, right? And it's at the bottom. And it's going to change along the length because EP changes along the length, right? And so that stress is going to be there. And then, I do say go in positive. It goes in positive, even though you're going to calculate it, because your S1 here, if you're going to the bottom, is going to be positive, and then it works out. The value you'll get is a negative number, though. And so just make sure that goes in as a positive. Yeah, applied load from the top, you get tension down at the bottom. Okay. Okay, that's their FPE value, different than our FPE value, right? FPC. Compressive stress in concrete after allowance for all pre-stress losses, so use the effective pre-stressing force, at centroid of cross-section, resisting externally applied loads, or at the junction of the web and the flange where the centroid lies within the flange. In composite members, we don't have composite members. So what this one is, compressive stress in the concrete after allowance for all pre-stress losses, so just use an FPE, at centroid of cross-section, resisting externally applied loads, or at the junction of this thing. Okay, so this is where, so it's a double T that you have going on, okay? This is what my stress calculations are, right? Negative FP over AC minus FPEP over S plus M external over S. The FP over AC gives us a distribution that looks like this. This one and this one, right? This is bending about the centroid, right? This is the stress that's coming from my pre-stressing, and this is the stress coming from applied loads. But if we look over here, if we break them down into these things, FPO, it's asking for the stress at the centroid, right? That's what this thing at the centroid over here. So it's asking for the stress here. What stress is our beam going to see at that location? Just this, right? It's just FP over AC for ours, right? Because these things are bending about the neutral axis, right? Or the centroid rather. They're bending about the centroid, so there's going to be zero coming from these things. So this, I mean, you could calculate if you wanted to, but this value is going to be 0, and this value is going to be 0. That makes sense, everybody? So it's really just saying this. So why all the other words? Right? Why didn't they just say it's FP over AP? Well, it's for some reason, if this centroid ends up in here, right, then it'll also have, right, so if my centroid was up here, you would actually have these values over here. These two values would actually be something. And they say to use it, that you're supposed to find it right at the joint between those two things. So you'd have, so the value's up here, but we're grabbing it at the joint. You'd have to grab it at the joint right there. That's what the problem. That's why there's the extra words there. But for us, it's just going to be this, FP over AC. But again, goes in positive. Even though we're going to get a negative value for that according to our equations, that goes in as a positive. And again, that'll be constant. That'll be constant along the whole length, right? Because all the other bending is going to happen about the centroid. It's not going to affect it. So that's just going to be the same value all the way. BW, right? One of the equations talks about BW, right? These things aren't actually shaped like this. If you look them up, they go like this. Well, that's exaggerated, but they go. Or something like that. They're wider at the top and narrower down at the bottom. Okay, and so what I would do, I would probably calculate BW average, right? The average the average width of one web, and then I would multiply that by 2 because you have 2 webs carrying the load, right? The other way to do it is cut your shear load in half. You can cut your demand in half and compare it to one of them, but I would just double my shear load because we have 2 webs. That's the better way to do it. Right? Does that make sense, that one? Why we do that? That's what I would do, because it's looking for that BW, but really BW, my width of my web varies over the height, and so just using the average I think works out well. Another value, stress due to unfactored dead load at extreme fiber of section where tensile stress is caused by externally applied load. So same thing, right? Stress due to unfactored dead load at extreme fiber where the tensile stress is caused by externally applied load. So that'd be my moment due to my dead load unfactored load divided by S1 in our case. Are you raising your hand or are you just doing that? Okay. Looks like I do say this. The flexure shear strength, VCI, shall be calculated the greater of A and B. And then it does look like I point over here. We have a non-composite uniformly loaded beam. The total cross-section resists all the shear, yes. The live load and dead load shear force diagrams are similar, yes. In this case, equation to and can reduce to this. So use these, take advantage of these simplifications if you can, right? Oh yeah, it says take advantage of the simplification. Usually implement also FD calc isn't required in this methodology. You don't have to do the FD calc. We're out of time, but I'm going to keep going here anyway. Yeah, you take advantage of this simplification if you can. Because these are things that always come up. Phi factor 0.75. I haven't said that in notes yet. The phi factor for shear is the same as the phi factor for regular reinforced concrete, which is 0.75. So that have to be there. Okay. If you're using your own ACI code, be careful. The section numbers have changed. The methodology stays the same, but that has changed. One of the things is, don't worry about this one right now. For one of the tables, that D over the D greater than 0.8 is eliminated for one of the methodologies. No, that's something else. And then here's the last thing. The distance from the centroid axis of the cross section. So this is what ACI says. ACI says this, YT in their equations is the distance from the centroid axis of gross section, neglecting reinforcement, to tension face. So the T in their case refers to the tension face. The PCI, this comes from the PCI design manual. That's their T talks about going to the top of the section, and that's going to the bottom of the section. So ACI's YT is PCI's YB. Great, right? Is what it is. This is just from years of me assigning this and working with the students. It's always one of these things that's a problem. So I figured if I hit it from the beginning, then maybe it'll save us as we go along. So the YB and the YT, be careful of those. They're talking Y bottom versus Y top. ACI is talking about Y tension is what their T stands for. Cool. Give it a go. It takes a while. So get on it. Get on it.
So leave it for the due date.
What's that?
Leave it for the day too.
Yeah, that's right. Yeah, that's what you always do.
That's what I did this week.
Are you working on it right now? Good.
I tried to do it yesterday. I have no idea what's going on.